البوشرية العالم علانة. جبت
I'm Guy McPherson of GuyMcPherson.com. Type in those letters, it'll take you to Nature Bats Last. And I'm going to comment on Sam Carana. As nearly as I can tell, Sam Carana is a natural scientist, and therefore he knows what he's talking about when it comes to the sciences. He has posted two very controversial pieces at the Arctic News blog in the last few years. Most notably, in the first case, he published a piece at the Arctic News blog on Friday, July 15th, 2016, titled A Global Temperature Rise of More Than 10 degrees Celsius by 2026. In a follow-up post, also at the Arctic News blog, posted on Wednesday, November 27th, 2019, titled Accelerating Greenhouse Gas Levels, Carana added 8 degrees Celsius to his previous 10-degree temperature increase. Now, I have commented on both of his posts, both of his blog posts, and I think the first one had it just about exactly right. I think the second one has it just about exactly right as well, if we assume the greenhouse gas equivalent of carbon dioxide increase. For example, in his second blog post that I have mentioned, Sam Carana mentions a paper by Schneider and colleagues published in Nature Geosciences on February 25th, 2019. It's titled Possible Climate Transitions from Breakup of Stratocumulus Decks Under Greenhouse Warning. In that paper, it is pointed out by Carana, and I'm going to read from the abstract, stratocumulus clouds cover 20% of the low-latitude oceans and are especially prevalent in the tropics. In the subtropics. They cool the Earth by shading large portions of its surface from sunlight. Here we report how stratocumulus decks respond to greenhouse warming in large eddy simulations that explicitly resolve cloud dynamics in a representative subtropical region. In the simulation, stratocumulus decks become unstable and break up into scattered clouds when CO2 levels rise above 1,200 parts per million. And if that figure applies also to the greenhouse gas equivalent of 1,200 parts per million, then I think Carana is absolutely correct and probably conservative in concluding the additional 8 degree Celsius global average temperature rise. The abstract goes on. In addition to the warming from rising CO2 levels, this instability triggers a surface warming of about 8K globally and 10K in the subtropics. Now, an 8 Kelvin temperature increase is exactly the same as an 8 Celsius temperature increase, so that makes perfect sense for Carana to reach that conclusion. I will continue from the abstract of the paper by Schneider and colleagues. Once the stratocumulus decks have broken up, they only reform once CO2 concentrations drop substantially below the level at which the instability first occurred. Climate transitions that arise from this instability may have contributed importantly to hothouse climates and abrupt climate changes in the geological past. Such transitions to a much warmer climate may also occur in the future if CO2 levels continue to rise. Again, I think Sam Carana is taking this information from the peer-reviewed literature and for the most part presenting a very conservative response in his posts. So I don't think we can remotely ignore these significant potential increases in global average temperature pointed out by Sam Carana.
Writing's not that.
Find feedback, prolonged Greenland Antarctic melting, and a consequent freeze event may ensue, lasting perhaps as long as 2 to 3 centuries. So it's going to be an oscillatory situation, is what he is suggesting here. 21st to 23rd centuries uncharted climate territory. Modeling of climate trends for 2100 to 2300 by the IPCC AR5 synthesis report in 2014 portrays predominantly linear models of greenhouse gas rise, global temperatures, sea levels. Wrong. We now know it's exponential increases. Therefore, the increase in temperatures, the increase in melting, increase in sea level that they estimate are going to be extremely underestimations. Extreme underestimation. So it's wrong. We now know it's increasing exponentially. So some of what they looked at, the albedo flip, what I just described, okay, so which increases the water surface area and sequestration of CO2, estimates a rise in radiative forcing due to removal of Arctic summer sea ice at 0.7 watts per square meter, a value close to the total of methane released in 1750. Reduced ocean CO2 intake due to lesser solubility of the gas with higher temperatures. Now, if you do introduce cold water into the surface, colder water will be able to absorb more CO2. So that's part of that back and forth oscillatory situation he was alluding to earlier. Vegetation desiccation loss in some regions. Dry areas get drier, wet areas get wetter, right? Reduce evaporation, which reduce evaporative cooling effects. Or increase precipitation, increase wetness in other areas. So you get differential feedbacks from the vegetation. Increase in wildfires that release greenhouse gases. Release of methane from the permafrost, bogs, sediments. Fracking, rice paddies. Linear temperature models do not appear to take into account the effects on the oceans of ice melt water derived from large ice sheets, including the possibility of a major stadial event such as already started in oceanic tracts fringing Greenland and Antarctica. In the shorter term, sea level rises, including the Greenland ice sheet, 6 to 7 meter level rise, and West Antarctic ice sheet melt, 4.8 meter sea level rise, referring to a major past stadial events, including the 8,200 years old Laurentian melt event and the 12.7 to 11.9 thousand years younger Dryas event. Prolonged breakdown of parts of the Antarctic ice sheet could result in major sea level rise, extensive cooling of northern and southern latitudes parallel with warming of tropical and mid latitudes. And that's according to a report by Hansen. The clashes between polar-derived cold weather fronts and tropical air masses will bound to lead to extreme weather events. Going back and forth, it's a battle here, but the overall thing is that overall the planet will still be warming. So at some point the warming will eventually probably win out. So, summary conclusions here. Global greenhouse gases have reached a level exceeding the stability threshold of the Greenland Antarctic ice sheet, melting at an accelerated rate. The current growth rate of atmospheric greenhouse gas of 3.42 ppm CO2 per year is the fastest recorded for the last 55 million years. And it's going to get faster. Allowing for the transient albedo enhancing effects of sulfur dioxide and other aerosols, mean global temperature has reached about 2 degrees C above pre-industrial temperatures. So the notion of keeping it below 1.5, as according to the Paris Accord, good luck. Due to hysteresis, the large ice sheets outlast their melting temperatures. Cold ice melt water flowing from the ice sheets at an accelerated rate will reduce the temperature of large ocean tracts in the North Atlantic and circum-Antarctic. Strong temperature contrast between cold polar-derived air and water masses and tropical air and water masses ensuing in extreme weather events would result in extreme weather resulting in extreme weather events, which retards agriculture in large parts of the world. Humans will survive in relatively favorable parts of Earth, such as subpolar regions, sheltered mountain valleys, where hunting of surviving fauna may be possible. But you ain't going to have no 8 billion people running around. In the wake of partial melting of the large ice sheets, the Earth climate would shift to polarized conditions, including reduced polar ice sheets in tropical to supertropical regions, such as existed in the Miocene 5.3 to 23 million years ago. Current greenhouse gas forcing and global mean temperature are approaching Miocene optimum-like composition, aside from the hysteresis effect of reduced ice sheets. Strong temperature polarities are suggested by the contrast between reduced Antarctic ice sheet and supertropical conditions in low to mid latitudes. Land areas would be markedly reduced due to sea level rise of approximately 40 plus or minus 15 meters, another underestimation. So what we're looking at here in this diagram is you have atmosphere CO2, you have global mean temperature. You can see a very nice correlation.
Very clear. Higher CO2 levels, higher temperatures. Lower CO2 levels, lower temperatures. Very straightforward, very clearly seen. We have the evidence for this.
That's shown in this graph here. Oh, okay. How can we sum this up here? Well, first of all, the IPCC once again is underestimating things. They're making the erroneous assumption of assuming a linear increase when it's exponential. So now the question becomes, and you've heard me make this argument, that if you melt enough of the Greenland ice, you can shut down AMOC and you can tip things into a cooler realm. That's kind of what they were saying here earlier. Because if AMOC slows down, and we are seeing the slowdown in AMOC, the Gulf Stream is going to slow down. Well, the Gulf Stream brings its warmth, gives it off, and that's why Scandinavia and the UK are warmer than they should be for their latitudes. That's going to stop. That's going to change. So you're going to see a market change between a polar region and lower latitudes. Right now, the gradient is blurred. So there isn't much of a temperature change. But as this melting continues and you add all that cold water to the surface, at first it's going to create this market difference. And that's going to affect weather. What happens after that is as the permafrost continues to thaw and add more CO2, now you're going to start heating up that surface water. Not to mention, you're also stratifying the ocean so that you're going to affect productivity, and that could lead to mass extinction. But you're going to start heating up that ocean surface, those upper layers that now have the cold meltwater, that's going to warm up. And that's going to take, this is how I interpret things, that is going to take us into the possibility of another hothouse Earth.
Ocean acidification has many detrimental impacts on marine life. Increased acidification causes decreased pH of the surface waters of marine systems, also causes coral bleaching, reduced calcification or dissolution of calcifying shell organizations, and decreased productivity. Ocean acidification also causes changes in species abundance and diversity of phytoplankton, in part a result of movement of phytoplankton to the poles. The uptake of iron in phytoplankton decreases with increasing acidification. How bad is it? I'll provide a brief overview in this video, and I encourage you to visit guymcpherson.com to find additional material embedded within the blog post coinciding with the release of this video. The shortest possible version of the existential threat we face comes from the abstract of a peer-reviewed paper in Marine Pollution Bulletin by Veron and colleagues. It was published in 2009, more than a decade ago, and it was titled "The Coral Reef Crisis, the Critical Importance of Less than 350 Parts per Million CO2." The abstract begins, quote, "Temperature-induced mass coral bleaching causing mortality on a wide geographic scale started with atmospheric CO2 levels exceeding about 320 parts per million," end quote. And then, from the final sentence of the abstract, referring to high levels of atmospheric CO2, quote, "This is likely to have been the path of great mass extinctions in the past, adding to the case that anthropogenic CO2 emissions could trigger the Earth's sixth mass extinction," end quote. We now know that we are in at least the eighth mass extinction event in the last 2 billion years. But at the time this was not known, we thought we were heading for the sixth mass extinction. James Hansen called for atmospheric carbon dioxide between 300 and 350 parts per million as a goal more than 30 years ago. We now know that 350 parts per million carbon dioxide in the atmosphere has led to numerous self-reinforcing feedback loops that point to a dire future for all life on Earth. Ocean acidification is one of several factors underlying the ongoing mass extinction event and also underlying abrupt, irreversible climate change.
And the point is, as was alluded, if you look at the next figure, the Earth is not a greenhouse. We don't have a barrier between us and space. But the way thermalization of the Earth and its equilibrium temperature goes is quite simple. A basic law of physics. Energy in equals energy out. And if you look at the next slide, incoming is solar radiation. Solar radiation is responsible for ultimately heating up the Earth, but the Earth then ultimately radiates energy back into space, an equal amount to what it absorbs, and when that happens, the Earth goes in equilibrium. The temperature of the Earth remains constant. It turns out the big misconception here is when you think about the greenhouse effect, it really has to do with not what's going on at the surface of the Earth, but what's going on at the top of the Earth's atmosphere. If you look at the left hand of those three block figures here, what happens is the Earth radiates an equal amount of radiation into space as comes from the sun when the temperature is the same. But where does it radiate? Well, if the atmosphere is opaque to the radiation it emits, you have to get to the very top of the atmosphere before it's transparent enough to emit into space. And that's what happens. The radiation is emitted into space from the top of the atmosphere. But there's a fundamental law of physics that the power a system radiates is proportional to the fourth power of its temperature. Now let's look at the middle figure. If we increase carbon dioxide in the atmosphere, carbon dioxide absorbs infrared radiation. That means the atmosphere becomes more opaque to radiation, and that means you have to go higher up in the atmosphere before it becomes transparent. So the atmosphere begins to emit radiation into space, not from where it did before, but now from a higher elevation. But higher elevations are colder. And if they're colder, that means the Earth is emitting less radiation from that higher elevation than it would have been had it been emitting its radiation from a lower elevation. And that means more solar radiation is coming in than is being re-emitted back by infrared radiation by the Earth. And that's what we now call radiation forcing. And we can measure that as well as calculate it. And we find that there's radiative forcing, that the increase in carbon dioxide is causing the Earth in the near term to radiate less into space than it absorbs from the sun, which causes the Earth to heat up. Ultimately, of course, you'll get to equilibrium again, as in the right-hand figure, where at that higher elevation, you're now at a warmer temperature because the Earth is warmed up, and now you're radiating into space an equal amount back to what you absorb from the sun. But in the process, from the top of the atmosphere right down to the Earth will have heated up, and we can calculate that effect. And so the net impact of this is that while we're not a greenhouse, while we have no rigid glass barrier, the fact that the Earth is radiating into space from the top of the atmosphere, and the fact that carbon dioxide causes the altitude at which the Earth is radiating to increase because the atmosphere becomes more opaque, means that the Earth is heating up. And we can calculate that, and in my book I show you how to calculate it, and we can predict how much the Earth will heat up. And we find even some very basic physics, without fancy models, you expect the Earth to have already heated up by about 1 degree Celsius in the last 60 years, and that's exactly what's been measured. I liken it more to a blanket in a sense than a greenhouse, because if you think of a blanket in a cold winter night, what's happening? Well, the surface of the blanket is much cooler than your body because the blanket is an insulator, and therefore the blanket is radiating much less radiation into space, into the room, than your body would be if you didn't have a blanket. And at the inner surface of the blanket, which is warm, the blanket is radiating that energy back to your body and keeping you warm. And more or less, that's what the atmosphere does, as I describe in the book. So those are 5 basic misconceptions that I've heard about the fundamental physics of climate change. And I hope I've given you some idea of the simple analysis of why they're misconceptions. And of course, in my book at great length, it's actually happily the book isn't too long, I try and describe to you and show you how you can actually understand the detailed physics, because it's basic science, and understand what predictions are ingrained in stone, like the sea level rise due to the heat we've put in, what predictions are likely, and what predictions are more speculative, so that you and hopefully our legislators can make more sensible estimates and decisions about what kind of policies we want to enact or don't want to enact as a result of increasing carbon dioxide in the atmosphere. Well, that's your Science Matters for this month, obviously impacted by the fact that I've written this book that's coming out this month. But when it comes to the global climate and human effects on the global climate, science really matters. And unless we understand the science, we can't possibly ever expect to have rational public policy. And that's why I wrote a book with the science. It doesn't discuss policy, just the science. And I think it's important, and not only is it important, but I think it's accessible.
Even some scientists can grasp, because some scientists, including me, have grasped the magnitude of the crisis that we face. I have great respect for the scholars I'm going to mention, the authors of these 2 papers, and what I'm doing here has nothing to do with defaming these amazing scholars. Rather, I'm pointing to evidence that I think has been overlooked in both of these papers. The paper in the conversation is co-authored by 2 of the, I believe it's 17 authors in the peer-reviewed journal articles Frontiers in Conservation Science. Okay, so first, paper in the conservation, again from January 13th, 2021, as is the peer-reviewed article. They get to the point right away. We provide a timely snapshot of the crises that must be addressed now. And also in the paper, they correctly point out that academics tend to specialize in one discipline, which means they're in many cases unfamiliar with the complex system in which planetary scale problems and their potential solutions exist. That's exactly right, as you would expect from the conservation biologist authors of this paper. They go on, more broadly, the human optimism bias, thinking bad things are more likely to befall others than yourself, means many people underestimate the environmental crisis. And I would add to that many people underestimate the environmental crisis because they know so little about the environment and how greatly we depend upon the environment for our own survival. And then toward the end, they point out that about 1 million plant and animal species globally are threatened with extinction. And actually, that's surprising because the lead author of this paper at the Conservation, Corey Bradshaw, is the author of the paper that points out that 5 to 6 degrees C increase in global average temperature will drive all life on Earth to extinction due to what he coins in that article with Strona, co-extinctions. So I'm surprised that this paper in the conversation underplays or downplays the magnitude of the crisis we face. Let's turn to the paper in Frontiers in Conservation Science. Again, this came out on January 13th, 2021. It includes authors that are among the best known, renowned, respected scientists on Earth. I know a few of them personally. I've interviewed others on the Nature Bats Last YouTube channel. I have great respect for all of these amazingly good scholars. The paper is titled Underestimating the Challenges of Avoiding a Ghastly Future, and what they're trying to do here is point out that we have underestimated for a long time how terrible the situation really is and is likely to become. And of course, it's only going to get worse. In the second sentence of the paper, they point out, we review the evidence that future environmental conditions will be more dangerous than currently believed. There's no question about that. We ask what political or economic system or leadership is prepared to handle the predicted disasters or even capable of such action. Not once in this paper do they cite any of the 5 peer-reviewed articles, at least 5 peer-reviewed articles by Tim Garrett, pointing out that civilization is a heat engine no matter how it's powered. I'm surprised and disappointed that this paper concludes that there is some way we can maintain civilization, maintain this set of living arrangements, and not continue to overheat the earth. That notion is unsupported by evidence. This dire situation places an extraordinary responsibility on scientists to speak out candidly and accurately when engaging with government, business, and the public. I couldn't agree more with that, and I think this is a classic case of downplaying the magnitude of the crisis. Okay, in one of the sections titled 6 Mass Extinction, apparently these conservation biologists are unaware that we're in the midst of at least the 8th mass extinction event on Earth in the last 2 billion years. There's no mention within this section of the August 2010 report from the United Nations Environment Program, pointing out that we drive an estimated 150 to 200 species to extinction every day. This goes back, in other words, more than 10 years. So for more than a decade, we've been in the midst of this mass extinction event, and we know that we've been in the midst of it. They go on to present very good evidence, but there is no mention of the aerosol masking effect, and there is little to zero mention of self-reinforcing feedback loops and the importance of those feedback loops. For the section subtitled Climate Disruption that begins on page 4, I'm going to turn to a relatively short essay that's in the sidebar or at the bottom, depending upon what kind of device you're using, of Nature Bats Last, GuyMcPherson.com. It's called Relevant Points for Interviewers, and there are about a dozen of these relevant points, and they're very short, and through links, they lead to additional information. For example, one of the points is, the rate of environmental change is reportedly 10,000 times faster than vertebrates can adapt, according to a peer-reviewed paper by Quintero and Weens, published in Ecology Letters on June 26, 2013. There's no mention of this paper in the new paper in Frontiers in Conservation Science. Again, the rate of environmental change is 10,000 times faster than vertebrates can adapt. That's hugely important given that we are vertebrates. Also, no mention of a paper by Davis and colleagues published in the Proceedings of the National Academy of Sciences on October 30th, 2018, that indicates mammals can't keep up either, and we're vertebrate mammals. That spells trouble to me. There's no mention of the paper by Burke and colleagues in the Proceedings of the National Academy of Sciences on December 26th, 2018, that the best analog for the future is the Pliocene, and that the Pliocene-style climate is coming as soon as 2030. In addition, this paper relies upon the representative concentration pathways of the Intergovernmental Panel on Climate Change, which notoriously downplay the magnitude of the crisis by excluding at least 6 dozen self-reinforcing feedback loops that we know about, and also never mentioning the aerosol masking effect or global dimming.